Hey guys, Buildzoid here, and today we're going to be taking a look at some behavior that I find kind of interesting about Intel CPUs with CEP functionality. So the motherboard I'm on here is a MSI Pro Z690-A DDR4 board. I have the 14900K in it. I've downclocked the CPU to 4.7 gigahertz because we're going to be running Prime 95 192K FFT size, and I don't want the CPU bouncing off of the power or the thermal limit. Because if it's bouncing off of either of those two limits, it just throws off the measurements. So, yeah, it's downclocked to 4.7 on the P cores and 3.2 on the E cores, because the E cores don't really matter for this test, and the P cores are the main thing driving the voltage. Um, but anyway, yeah, and so the behavior we're going to be taking a look at is how CEP affects voltage regulation. Because it actually is, you'll see. But so first we're going to do disabled CEP. Um, and the setup that I'm running here, we do have a slight, very, very slight voltage offset at the VRM. And the reason for this is that I wanted to get CEP to trigger sort of sooner and more consistently. Because the way CEP works is it basically triggers whenever the voltage at the CPU is too far away from the target voltage that the CPU thinks it should be getting. So by applying this 10 millivolt offset, we basically eat into that margin before CEP triggers, right? And I don't know where exactly the trigger point is, but there's like a few millivolts that you can lower the voltage before CEP starts kicking in. So this is just to make it kick in a little bit more consistently. It could probably go maybe even lower than that, but I didn't want to spend a bunch of time like fine tuning it. Like it seemingly still worked. Like the demonstration seemingly still would work even with like a 15 millivolt offset, but yeah, there was some weirdness showing up on the oscilloscope, which might have just been the operating system doing operating system things. But anyway, the VRM is set to mode 1. Oh, the other reason that the CPU is downclocked is because Prime 95 with 192K FFT size makes this motherboard reset itself. I think it's tripping some kind of overcurrent protection or something, because yeah, you run Prime 95 and the board just resets after a random amount of time. So that's kind of fun. Um, I have the switching frequency lowered. I have the overcurrent protection maxed out. It's not like there's really there's auto and enhanced, and I don't like it doesn't it seems to me that enhanced isn't quite enhanced enough, but then again the VRM on this board isn't particularly amazing. So yeah, so there's no V droop, right? So the VRM has no V droop, and the CPU does know that there's no V droop. The AC load line is set to 1, the DC load line is set to 1. And so yeah, we're going to do this initial run with CEP turned off to sort of see what happens if the CPU doesn't start clock stretching when the voltage is way too low. And then we're going to turn CEP on, and you're actually going to see that there's less undershoot, which makes sense, but it's just kind of it's just kind of cool that we can actually see this behavior. Um, So really, actually, CEP, the current excursion protection, technically it will pick up peak currents, but really what it reacts to most of the time is excessively fast ramps in output current. Like if the current draw ramps up too quickly, the voltage will drop, and that'll trigger CEP. So anyway, we're going to run 192K FFT size with all of the AVX turned on. This is going to run on all of the cores. So this is actually in this configuration of 4.7 gigahertz. With the admittedly, we're just using the stock vid table for the CPU. So we're running a lot of extra voltage because the factory vid tables from Intel run heaps and heaps of extra voltage as reliability margin basically. But yeah, so with this configuration, the CPU actually pulls 230 watts, which is kind of surprising that yeah, even at 4.7 it can get that freaking power hungry. Anyway, so here we go. And as long as I'm not moving the mouse, no big deal. We just have the usual Windows interrupt, like Windows event timer interruptions in the workload, and those cause that like overshoot spike, which CEP really doesn't care about that. Like the voltage going up is not CEP's problem. CEP's problem is when the voltage suddenly dives off a cliff, or if the voltage is just too low in general, which is why it like messes with undervolting if you're undervolting at the voltage regulator, because the CPU thinks it's going to get 1 voltage and then it gets something like 100 millivolts below that, and CEP gets very upset. But anyway, so we do actually need to give this a little bit of a warm-up period, I've found, because, and I'm not sure, it might just be like the power plane heating up. But yeah, like depending on how soon I start messing with this, after it starts, like it gives slightly different results. But anyway, so yeah, now if I move the mouse around, because Windows is basically like processing the mouse input, you can see that we get these massive undershoot spikes, right? Because every time Windows goes to process the mouse, like it just stalls out the Prime 95 process, and then once it finishes processing whatever the mouse is doing, Prime 95 ramps all the way back up to 100% load, which creates these massive downward voltage spikes. So I'm actually going to put there. So yeah, and so that looks really, really ugly, right? Because we basically get this like repeated, like this right here is Prime 95 doing its thing, pulling all of the power in the world, and then I touch then the mouse moves and Windows freaks out and stalls Prime 95 out, which this VRM isn't very good as far as voltage regulation is concerned. So yeah, the VRM seemingly, like, to be fair, actually, you see something similar on most boards where it like kind of freaks out for processing the mouse input, because you're still gonna have like Prime 95 and like the mouse are gonna be kind of running at the same time, because you don't need all of the cores to process mouse input, right? But yeah, so we get this like freak out event over here, and then once Prime 95 resumes, the voltage is just like, it's just fallen off a cliff. So the voltage ends up really, really low. Anyway, so we're just going to zoom back out to 5 milliseconds per division. I am going to save this waveform as a reference, and then we're going to turn CEP on, and, yeah, we're just not going to... We're not going to see any more, like, this. Yeah, so I'm just going to stop the workload now. And we're going to shut down and restart, and we're actually going to just see less undershoot, because basically when CEP detects that the voltage is like way too damn low, it slows the CPU down, which means the like Prime 95 doesn't get to ramp as hard in terms of the workload. So yeah, this basically puts less, like CEP basically puts less stress on the motherboard's voltage regulator, and it should improve CPU stability. On top of whatever, like, Intel seems to have some other, like, clock stretching functionality built in as well, because you can, like, the whole, like, 13th gen, 14th gen doesn't seem to be super sensitive to undershoot from, like, a stability perspective. Like, that seems to be true even when CEP is turned off. So this seems like another layer of, like undershoot tolerance built into the CPUs. Or, like, this doesn't even... Technically, it'll actually help with, like, the CPU downclocks when the voltage gets too low, so the CPU is less likely to crash because it's downclocked. But also, it reduces how much undershoot there is. So the voltage doesn't dip as far, and that also helps stability. Though, funnily enough, if you're undervolting with vid offsets, you can still crash CEP. Like, you can still make the CPU crash. Like, CEP is, like... Yeah, like, it doesn't... It's not a magical, like, oh, CPU will always be stable type thing. It's just... It makes the CPU power delivery requirements somewhat easier to achieve. So anyway, we're now going to turn CEP on. And basically, I'm not... Like, this trigger, the trigger level that I have on the scope right now, so the trigger's right here, which is 1.06 volts. Like, we're not actually going to catch any spikes that go that low anymore. So, Yeah, and I'm just kind of excited that like you can even see this behavior. Now, in theory, if you had a better motherboard, this would be less pronounced, like this behavior. Um, and if you had a worse motherboard, it would get more pronounced. And this motherboard really isn't that like, it's not an Apex. And I'm kind of suspect. I think most of the Gigabyte boards I have are better in terms of voltage regulation. Though I like doing A/B comparisons between motherboards when you're measuring the voltage from the back of the CPU socket isn't super reliable because you don't know how like if the impedance to the back of the socket is consistent across all of the boards. Like one more, and I don't think like MSI would be like, oh, there's less via stitching, like less stitching of the power planes on this board than like some of the high-end boards, but also this is like a 6-layer PCB. Um, so just like the resistance of the power planes, especially once it gets up to temperature, are going to be different, which is why I actually have a VR, like a fan on the VRM for this testing, because if you just like without because if you actually just let the board heat up over time, like your voltage measurements from the back of the board will change because the resistance of everything is going up as the temperature increases. So, um, yeah, that's like like weird measurement things that you sort of have to consider. Is that like if you're measuring somewhere on the power planes, and actually I wanted to do this as like a video, is like measure like hook up a whole bunch of voltmeters to like different inductors on a VRM and then also onto like the back of the socket. Actually, I guess I could just use all 4 channels on my scope to do that. Yeah, I could totally do that. Just hook up. Actually, the coax is really annoying for that. The inductors don't generally. Well, a lot of motherboards have little multi-layer ceramics on the backside that I could go for. So yeah, I could like run like you could basically my idea was like it would be kind of cool to like plot the voltages diverging as the power plane heats up. So the voltage at the CPU socket would like slowly rise as the power plane gets warmer, but the voltages at the different inductors in the VRM, like say you have like a 16 phase, right? And you have like one inductor that's really close to the socket and then you have some inductors that are really far away. So you would see as the power plane heats up, the far away ones would end up with significantly higher voltages on their output than like the one nearest to the socket, and even the socket would slowly start rising in operating voltage over time. Um, but anyway, that's not the point of this video. That's just like a random thought that I thought would be kind of interesting to look at. Um, Anyway, 192K FFT size, but this time with CEP turned on. Now, right at the start of the test, this isn't actually CEP, like this is just the start of the test. It doesn't, like, for some reason, there's like a ramp period to this for some reason. So yeah, like right at the start, like there's just not very much undershoot. And after it's been running for a while, it starts getting progressively worse and worse, but it's never going to get as bad as the configuration without CEP. Which I just think is neat. Like that's literally all there is to this video. I just think it's kind of neat that we can measure that. Also, I should have probably started Prime 95 while rambling about like power plane thermal effects. So yeah, now we're getting some serious like undershoot, but you'll notice it doesn't get as low as that reference waveform I saved. And like we could run this for an hour and it's never going to get as low as that reference waveform. Like if I tried to trigger on that, I can't. Cuz CEP will not let the voltage undershoot that hard. Which I just think is kind of neat. I'm not sure there's any actual practical upsides to this from like a stability perspective, because like I mentioned, if you're undervolting, CEP won't, like if you're undervolting through vid offsets, CEP won't save you from the voltage being too low. Right? CEP only like blocks CEP only blocks, like only reacts if the voltage is too low relative to what the CPU is expecting. So if you tell the CPU, hey, offset your 5 gigahertz vid request by 100 millivolts, well, the CPU expects it to be 100 millivolts lower, so CEP isn't going to do anything about that, right? Whereas if you tell the VRM to offset the vid request by 100 millivolts, CEP gets very upset because the CPU isn't aware that there's this 100 millivolt offset. But anyway, so yeah, like I actually just can't trigger on this anymore, right? And I guess just to prove the point, I'm going to go back into the BIOS, switch CEP off again, and then the trigger is going to start working. Like I'm not going to, you know, like touch anything. I'm just going to turn CEP off, and then we're just going to see if the trigger starts catching stuff again. Because, yeah, like when CEP is on, like it doesn't prevent all of the undershoot, right? Like you did see that the voltage was still diving. It just didn't dive anywhere near as hard as it does when CEP is turned off, which I just think is kind of neat. And I guess this actually, like NVIDIA GPUs would technically have the same effect with their built-in clock stretching functionality, and actually Ryzen CPUs as well, where like, yeah, because the thing is, like, the amount of current the CPU pulls is directly tied to the frequency that it's running at, right? So if you temporarily drop the clocks, like if you cut the frequency in half for like a short period of time, you've literally just cut the power consumption in half. Right? So the maximum current, like your current draw, literally gets cut in half. Or not actually exactly in half, but basically very close to in half. So, and I'm not sure how drastic the clock stretching gets. I've kind of wondered about, like, if you ran a test of like an intentionally like okay, so yeah, you can see how we're at the start, like we're not getting those massive downward spikes. So we need to wait for a bit. Eventually, like, it'll ramp up. I didn't remember to disable it, right? I find it kind of interesting how the, like, that transition eventually happens where it, like, starts spiking really bad. We're still not there yet. Oh, there we go. Yeah, now we're seeing it. I wonder why it takes so long for this behavior to start showing up. Like, I wonder if it's like something warming up. I think it's a thermal effect. Like something on the motherboard has to warm up, and then you start getting this. Anyway, now if I put the trigger on single, bam, right? Like it catches it. And you turn on CEP, and this doesn't happen anymore. So yeah, I just think that's really neat, and I wanted to make a video about it because yeah, like, cool. Now, from a stability perspective, I don't like if you're undervolting through vid offsets, this literally doesn't do any. Or maybe it'll let you run a more aggressive AC load line. Like if you set your AC load line to 1 and your VRM load line to 0, right? And by what I mean 0.01 milliohms. So 10 microohms. Yeah. So if you set the load line to like 10 microohms and your VRM V droop to 0, it might be more stable with CEP turned on, maybe. I'm not sure because again, like I mentioned in the past, like I've really struggled with actually getting 13th gen, 14th gen CPUs to crash due to undershoot in general. So I kind of suspect that there's some more clock stretching functionality built in that isn't directly tied to CEP. Yeah, I still think this is really neat that like we can, like measure this effect of like, hey, it reduces the undershoot by quite a significant margin. So yeah, anyway, that's it for the video. So thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that in the description below as well. And that's it for the video, so thanks for watching, and goodbye.